It is unusual to have provisions for future circuit breakers that are significantly larger than the existing breakers in a panel. Here are a few reasons why it might seem pointless. Firstly, oversizing. Providing provisions for circuit breakers that are much larger than the current load requirements suggests that the engineer is unnecessarily oversizing the panel. This could result in wasted space and increased costs. Secondly, compatibility. Circuit breakers are designed to work with specific panel ratings. Installing larger circuit breakers may require replacing the entire panel or making costly modifications. Thirdly, future load uncertainty. It is difficult to accurately predict future load requirements, especially for lighting circuits. Specifying oversized circuit breakers based on hypothetical future loads may not be a prudent use of resources. Fourthly, National Electrical Code requirements. The National Electrical Code does not typically require provisions for future circuit breakers that are significantly larger than the existing breakers. However, there could be specific reasons why the engineer is requesting these provisions. For example, expansion plans. The engineer may be anticipating future additions or renovations that would require additional electrical capacity. Also, redundancy. Providing extra circuit breaker spaces allows for future expansion or redundancy in case of a circuit failure. Furthermore, flexibility. Having the ability to add larger circuits in the future provides flexibility for unforeseen electrical requirements. It is advisable to discuss these provisions with the engineer to understand their rationale and ensure that the design meets the actual electrical needs of the facility. The seemingly odd request for a 125 amp 480 volts panel with provisions for two 225 amp and two 100 amp future circuit breakers might raise questions about its necessity and cost effectiveness. Several factors could explain this design choice, even if it appears unusual at first glance. Let's delve into these considerations. First, consider future expansion. One of the most common reasons for oversizing electrical panels and including provisions for future breakers is to accommodate anticipated future load increases. If the school plans to add more lighting equipment or entire wings to the building, having the capacity readily available can save significant money and disruption later on. Installing larger conduits and panels upfront is much cheaper than retrofitting the electrical system when the new loads are actually needed. Second, there's redundancy and reliability. In critical facilities like schools, maintaining electrical service is paramount. Having spare breaker capacity allows for quick and easy circuit rearrangement in case of a failure. For instance, if a breaker trips and needs replacement, a spare breaker can be used to restore power while the faulty breaker is being repaired or replaced. This minimizes downtime and ensures continuity of operations. Third, flexibility for unforeseen needs. Even with careful planning, it's impossible to predict all future electrical requirements. Having extra breaker capacity provides flexibility to accommodate unforeseen needs that may arise. For example, a new type of equipment might be introduced that requires a dedicated circuit, or a classroom might be repurposed into a lab with higher electrical demands. Fourth, voltage drop considerations. Longer circuit runs can experience voltage drop, which reduces the voltage available at the load. To compensate for voltage drop, it may be necessary to use larger conductors and correspondingly larger breakers. This is especially important for lighting circuits, as excessive voltage drop can cause dimming and reduce lamp life. Fifth, code compliance. While the National Electrical Code does not explicitly require provisions for future breakers of a specific size, it does mandate that electrical systems be designed to handle the anticipated future load. Local codes or regulations may also have specific requirements for spare capacity in electrical panels. Sixth, standardization and availability. It may be more cost-effective to use a standard panel size with readily available breaker sizes than to custom order a smaller panel with limited capacity. Standardized components are typically cheaper and easier to source, and they may also simplify maintenance and repairs in the long run. Seventh, engineering judgment. Ultimately, the engineer is responsible for designing a safe and reliable electrical system that meets the needs of the facility. They may have specific reasons for oversizing the panel and including provisions for larger breakers, based on their experience and understanding of the project requirements. It's always a good idea to discuss these design choices with the engineer to understand their rationale and ensure that the design is appropriate for the application. Now let's analyze the specific breaker sizes in question. The engineer is specifying a 125 amp 480 volts panel with provisions for two 225 amp and two 100 amp future breakers. This configuration does seem unusual, as the future breakers are significantly larger than the existing panel capacity. Here's a breakdown of the potential reasons for each breaker size. The 225 amp breakers could be intended for large pieces of equipment that may be added in the future, such as HVAC systems, industrial machinery, or electric vehicle charging stations. These types of loads can draw significant current and require dedicated circuits with appropriately sized breakers. The 100 amp breakers could be intended for smaller but still substantial loads, such as additional lighting circuits, receptacles, or small appliances. These breakers may also be used to supply sub-panels that serve specific areas of the building. It's important to note that the total load connected to a panel should never exceed the panel's rating. Even though the panel has provisions for larger breakers, the total load in the panel must be carefully managed to prevent overloading and potential hazards. In summary, while the request for oversized breakers may seem unusual, there are several valid reasons why an engineer might specify this design. These reasons include future expansion, redundancy, flexibility, voltage drop considerations, code compliance, standardization, and engineering judgment. It's always best to discuss these design choices with the engineer to understand their rationale and ensure that the design meets the actual electrical needs of the facility. Now let's consider the National Electrical Code, or NEC, requirements related to panel sizing and overcurrent protection. The NEC provides detailed guidelines for calculating electrical loads and selecting appropriate conductors and overcurrent devices. Article 220 covers branch circuit, feeder, and service calculations, which are essential for determining the proper size of electrical panels and breakers. Section 220.100 provides guidance on general requirements for branch circuit, feeder, and service calculations, emphasizing the need to consider all connected loads and any applicable demand factors. Demand factors allow for reducing the calculated load based on the assumption that not all connected loads will operate simultaneously. This can result in a smaller panel size and low material costs. Section 220.12 provides specific requirements for general lighting loads, which are relevant to the lighting circuits mentioned in the question. The NEC specifies a minimum lighting load of 3.5 volt amps per square foot for schools, but this value may need to be adjusted based on the type of lighting used and any applicable energy codes. Section 220.51 covers receptacle loads in non-dwelling units, requiring a minimum load of 180 volt amps per outlet. This value should be used for calculating the load of general-purpose receptacles in classrooms, offices, and other areas of the school. Article 240 addresses overcurrent protection, providing requirements for selecting and installing fuses and circuit breakers. Section 240.4 specifies the protection of conductors, stating that conductors must be protected against overcurrent in accordance with their capacities. This means that the overcurrent device must be sized to protect the conductor from overheating or damage. Section 240.6 lists standard ampere ratings for fuses and circuit breakers, which are typically available in increments of 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, 700, 800, 1000, 1200, 1600, 2000, 2500, 3000, 4000, 5000, and 6000 amps. Section 240.21 covers location in circuit, stating that an overcurrent device must be placed at the point where the conductor receives its supply. This ensures that the conductor is protected against overcurrent throughout its entire length. Article 310 provides requirements for conductors for general wiring, including ampacity ratings and installation requirements. Section 310.15 specifies the ampacity of conductors, which is the maximum current that a conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation method. Tables 310.16 through 310.21 provide ampacity ratings for various types of conductors based on different insulation types and installation conditions. These tables are essential for selecting the proper conductor size for a given load. In addition to the NEC requirements, local codes and regulations may also have specific requirements for electrical installations. These codes may be more stringent than the NEC and must be followed to ensure compliance. Therefore, it's essential to consult with local authorities and inspectors to determine the applicable codes and regulations for the project. In the context of the question, the engineer's request for a 125 amp 480 volts panel with provisions for two 225 amp and two 100 amp future breakers should be evaluated based on the NEC requirements and any applicable local codes. The engineer should provide documentation to support the design choices, including load calculations, conductor ampacity calculations, and overcurrent protection coordination studies. This documentation will help to demonstrate that the design meets the applicable code requirements and provides a safe and reliable electrical system for the school. Let's discuss the practical implications of installing oversized breakers in an electrical panel. While having extra capacity can be beneficial, it's important to consider the potential drawbacks and ensure that the installation is done correctly. Firstly, consider cost. Oversized panels and breakers can be more expensive than smaller ones, so it's important to weigh the cost against the potential benefits. If the future load requirements are uncertain, it may be more cost-effective to install a smaller panel initially and upgrade it later if necessary. Secondly, space requirements. Oversized panels can take up more space than smaller ones, which may be a concern in areas with limited space. It's important to consider the available space and ensure that the panel can be installed safely and conveniently. Thirdly, coordination issues. Oversized breakers can create coordination issues with other overcurrent devices in the electrical system. Coordination studies should be performed to ensure that the breakers will trip in the correct sequence to minimize the extent of any power outages. Fourthly, maintenance considerations. Oversized breakers may require special tools and equipment for maintenance and testing. It's important to ensure that qualified personnel are available to perform these tasks. Fifthly, safety concerns. Oversized breakers can create a false sense of security, leading to overloading of circuits and potential hazards. It's important to educate users about the limitations of the electrical system and the importance of not exceeding the panel's rated capacity. Furthermore, let's elaborate on the different types of loads that might be connected to the future breakers in the 480 volts panel. For the 225 amp breakers, potential loads could include large HVAC equipment, such as chillers or air handlers. These units can draw significant current, especially during startup, and require dedicated circuits with appropriately sized breakers. Another potential load for the 225 amp breakers could be electric vehicle charging stations. As electric vehicles become more popular, schools may need to install charging stations to accommodate staff and visitors. These charging stations can draw significant power and require dedicated circuits with high ampacity ratings. Additionally, the 225 amp breakers could be used to supply large kitchen equipment, such as ovens, stoves, or dishwashers. These appliances can draw significant current and require dedicated circuits to prevent overloading. For the 100 amp breakers, potential loads could include additional lighting circuits. As schools upgrade their lighting systems to more energy-efficient LED fixtures, they may need to add additional circuits to accommodate the increased number of fixtures. Another potential load for the 100 amp breakers could be receptacle circuits in classrooms or labs. These circuits can be used to power computers, projectors, and other electronic equipment. Furthermore, the 100 amp breakers could be used to supply small HVAC units, such as window air conditioners or portable heaters. These units can draw a significant amount of current and require dedicated circuits to prevent overloading. It's important to note that the actual loads connected to the future breakers will depend on the specific needs of the school and the types of equipment that will be used. The engineer should work closely with the school to determine the appropriate breaker sizes and ensure that the electrical system is designed to meet the school's current and future needs. Finally, let's discuss the importance of documentation and communication throughout the design and installation process. Proper documentation is essential for ensuring that the electrical system is installed correctly and can be maintained safely and effectively. This documentation should include load calculations, conductor and capacity calculations, overcurrent protection coordination studies, panel schedules, and wiring diagrams. The documentation should be readily available to maintenance personnel and should be updated as needed to reflect any changes to the electrical system. Communication is also essential throughout the design and installation process. The engineer should communicate clearly with the school about the design choices and the reasons behind them. The contractor should communicate clearly with the engineer and the school about the installation process and any potential issues that may arise. Open communication will help to ensure that the electrical system is installed correctly and meets the needs of the school. In conclusion, the engineer's request for a 125 amp 480 volts panel with provisions for two 225 amp and two 100 amp future breakers may seem unusual, but it's important to consider the potential reasons behind this design choice. These reasons could include future expansion, redundancy, flexibility, voltage drop considerations, code compliance, standardization, and engineering judgment. It's always best to discuss these design choices with the engineer to understand their rationale and ensure that the design meets the actual electrical needs of the facility. By following the NEC requirements, communicating effectively, and documenting the design and installation process, you can ensure that the electrical system is safe, reliable, and meets the needs of the school for years to come.